let's try to solve this. Actually, not solve, but let's work on this circuit problem here. So it says write enough KVL, KCL equations to solve. So we're not going to do all the algebra, but we're going to write the equations we need so that if we had the time and motivation, we could solve. Okay. So when we're doing a problem like this, what do we want to do first? Well, we want to write equations. To write equations, we need variables. So we need to go ahead and label and name the variables that aren't given to us in here. So notice this circuit, it has sources spread throughout the circuit. So the resistors really, there's nothing in series, nothing in parallel. So we can't really do the parallel series combination stuff here. And so we're going to have to do KVL and KCL, and that's what it told us to do anyway. All right, so we've got our source, and so we would kind of generally, to get the current flow directions, although this isn't going to work perfectly, but make positive sign or draw our currents coming out of the positive terminals of all of our sources. And we can go ahead and remember that the long side of a source is a plus, of a battery symbol like this. Long side is plus. And so we make the currents come out of the pluses of all of our sources. And I guess we can just name them I1, I2, I3. I'm going to run out of room, I'm afraid. But hopefully we'll be able to see stuff here. Okay. Current flow that way. Okay, and so then we need to have voltages for all of our resistors. And we're going to have trouble. So we want to do positive sign convention. So for resistors, positive means current comes into the positive. So we're going to name the voltage, or we're going to label the voltages here. Let's just go ahead and put plus and minuses on all our resistors. The current's coming into the bottom, so plus and minus like this. For this one, this source is in series with this resistor, so the current is going this way in this loop, right? Continuing the flow there. And so the plus side would be here, minus side would be here. These don't have defined currents yet, so we would need to take a guess at those. And I don't know. This one, we have current coming in, so maybe it makes sense that the current will be going this way. So we'll name that, we got 3, we'll call this one I4. That's a 4. And then if these two are coming in, maybe this one's going down. So we'll name this one I5. And I don't know about this one. So we've got current coming in here, going out there, going out, going out. We don't really know. I'll just take a guess. We'll call I6 this way. All right, so now with respect to these currents that I've named, then this resistor, current comes in this side, so this is the plus side. Minus side on the other side. Here, current's coming in, going out there, so that's the minus side, and going in the plus over here. And again, plus and minus for this one. All right. And so, this kind of looks like another plus, but that's the minus side up there. And we could give these all names, all the voltages names, or we could name them in terms of Ohm's law. So let's go ahead and name them in terms of Ohm's law this time, just so we can write our equations easier. And so voltage is V equals IR. V equals IR, and these are the voltage. We want to name the voltage, so we want I times R for this resistor is I1 times 5, because its current is I1, resistance is 5. R is 5, I is I1. So we would say, let's just call this voltage 5I1. So it's kind of weird. It looks like a voltage. Maybe we should go ahead and name it too. Let's go ahead and name them. V1 is 5I1. Okay. Let's say the voltage on this resistor, let's say that's V2, and it is going to be what? According to Ohm's law, I2 times 4. So 4I2. This voltage here, we'll call it V3. And it is going to be, in terms of Ohm's law, I4 times 3, so 3I4. Oh, what a mess. Okay, this voltage across the 1 ohm resistor, we'll call that V4. And that's going to be equal to 1I5. Over here, The current is I3. Let's see, we'll call it V5 is equal to 7I3. All right, and finally this one down here, we can call it V6, and it is equal to 2I6 for its Ohm's law. Did we get everything named? I think so. So, how many equations do we need? Well, since we've written all of our voltages that we don't know in terms of currents, we'll just have to count the currents. So we have I1, I2, I3, I4, I5, and I6. Right, so we got 1, 2, 3, 1, 2, 3, 4, 5, 6. 6 different kind of branches with some stuff maybe in series with it, but 6 different separate branches of the circuit that could have current. So 6 different currents. So we have 6 unknown currents. It means we need 6 equations. All right, we can get them from KVL and KCL kind of things. So let's just start with the KVL on the left loop, we'll say. KVL left. All right, so we're going to remember KVL, Kirchhoff's voltage law, sum up the voltages. We walk around the loop, whatever side we hit first on the voltage, we put that sign on it in the equation. So we're going to have negative Vs. If we start right here and walk around, negative Vs plus V1, but V1 is 5I1, so I'm just going to write 5I1 in here. All right, plus 5I1, we get in the plus side. If we come down around here, we're going to hit the negative side of this guy first. So it's going to be minus, and then we call that V2. We could write minus V2, but we're trying to write it in terms of just the current, so we'll say minus 4I2 for that voltage, right? 4I2 is a voltage, right? Even though it seems like it's a current, but we multiply current times resistance, we get voltage. All right, and then we're coming back through here. We hit the plus side of Vx. We'll assume that's a known voltage. It's not adding another variable. Comes back to where we were, equals 0. Okay, so there's one equation. 1. Number 2, KVL. Let's do middle, I guess. Okay, so we'll start here and go around. So starting here now, we go through this voltage source. We hit the negative side first. So it's going to be negative Vx. Coming up, we're going to hit the plus side of this resistor. So it's going to be plus V2, which is 4I2. So plus 4I2. Continuing around, we hit the plus side of this 3 ohm resistor first. So it's plus V3, but we're not writing in terms of voltage, we're writing in terms of current. So 3I4 plus 3I4. Continuing on down around the loop, come through here, we hit the plus side first, so it's a plus. And this one is called 1I5. And then continuing on around here, we hit the 2 ohm resistor, plus side first, so plus, and its voltage was 2I6. Continuing on, we got to where we started, equals 0. All right, 2 equations. We got a ways to go. Let's do number 3, KVL right. Go around this loop. So if we start here, we go up through the minus side of that first resistor, so that's going to be a minus, and that one is called 1I5. Yeah, that's a 5. 1I5. Continuing on around, we get to the plus side of this voltage source first, so it's going to be plus Vy. Again, Vy is assumed to be a known thing. Usually we know what the battery voltages are. Easy to measure anyway. And then we come around here, we hit the negative side of our V5, but we're not running V5, we're running IR version, so 7I3. We came back to where we started, equals 0. Alrighty, we got 3 KVL equations. And we could write some more KVL equations for different loops, different paths around. But let's work on KCL equations because I think they tend to be more independent. Right? We might get the same, might not get linearly independent equations when we do more loops. So let's look at the nodes. So we've got a node here. It's a boring one. It only connects 2 things. We've got a node here. that connects three things, right? All of this is one big node. Think of it as a Play-Doh. We could mush it or squish it to be whatever shape we wanted, but it connects those three things. We have another node here that connects three things, right? We have this node. Oops, I want a different color. We have this node that goes, so the nodes have to go until they hit something that's not wire, right? So this node connects 1, 2, 3 things. What color? We have another node here that's a boring one, only connects 2 things. We have this node here that connects 3 things also. All right, so we have 4 different nodes that connect. They all connect 3 things. Okay, some nodes could connect 4, but I didn't make any in this circuit, I guess. And so let's write some KCL. So let's do KCL red. We'll call it KCL red. Bottom left here. So what do we have? We have KCL, we're doing in equals out. So I1 goes up through this voltage source, so it's coming out of this node. I2 is coming out, but I6 is coming through this resistor, coming into this node. So for the in, we'll have an I6. That's the only thing coming in. And going out is, like I said, the other two, I1 plus I2. All right, looks good. How about KCL on the blue? What happens here? Okay, so we got I1 continues on around, comes through this resistor, goes into the blue. I2 comes up through this resistor into the blue. I4 goes out, goes to the right through that resistor. So now we've got 2 ins. I1 plus I2 are going in, and I4 is going out. Okay, that looks like a good equation. I'm going to skip a row here. KCL, which one should we try? Orange or blue, green? Let's do green. Okay, so coming in, what do we have? We got I5's coming down through this resistor, so it's coming into the green. I6 is going this way, so it's going out through that resistor. And I3 is going up and out that way. So we got only one in again, which is I5. So that's the in, and then the outs are I3 and I6. Okay, so that looks like a good set. So this was 4, 5, 6. And so I think they're all linearly independent. They don't relate. So the node currents have different currents in them, so I would say they're not related. And I'm pretty sure when we do meshes like, or loops like this, that we get an independent set. So I think we're all good. So we've got 6 equations, 6 unknowns, and so that is good for the first one. All right, so we could, given numbers for the voltage sources, we could do a bunch of algebra, figure out what all 6 of those currents are. All right, maybe not fun, and we're not going to do it right now, but it's possible. Okay, if you would write a set of 6 and you find out that, oh, this equation is really the same, you know, these two combined really give the same equation again, and it's not linearly independent, find another node, write another KCL equation, or try a different loop, find another equation. Okay, let's try this circuit. So what's weird about this circuit? Well, what's different is that it has resistors and capacitors. Now what's going to happen? All right, so we have to, well, KVL, KCL still hold. So let's go ahead and name stuff. And so let's go ahead and put, starting with our source, get a current direction. All right, so we call this IS, I guess. And then let's just go ahead and say, my printer keeps resetting here, but hopefully we're okay. Say the current just, if it comes up through here, it's probably going to go back around the other way. There are no sources in these branches, so we'd expect current to come out of the source and then flow around. All right, so let's just call this I left and I right. Good enough names. Okay, and so we're going to assume, since capacitors are funny, they'll charge up and they'll block the current. So if they charge for a while, and then they'll get to a limit of when the voltage is matched, and then they'll stop the current. So we kind of make a switch like this and say at time t equals 0, the switch closes, and then we're going to see what happens. So this circuit is going to have a transient. It's not just going to be a constant kind of thing. We're going to watch what happens as the capacitor charges up kind of thing. So basically what happens when we have R's and C's in the same equation is that we're going to have differential equations to deal with, and so we're going to have time dependence of things, and so the current and the voltages can be functions of time, and we have differential equations to solve. All right, but today we're just writing equations, so we'll be okay. All right, so let's see. Continuing on, we still need some things named. So let's go ahead and name this voltage V1, and notice I put the plus. Current comes into the side of the resistor, so I put a plus on that side. Same thing here, we're going to name this VC. Capacitors are also loads, just like resistors. They don't have sources inside of them. And so their positive sign convention would be current comes into their plus. So you put a plus on the side where the current goes in. Similarly, this R2, we call it V2, I guess. All right, so I think we have everything named or a value for them. So we're good to write equations. We probably have a few more things than we need, right? So we would probably want to just call this IR1, ILR1. Let's give myself a little more space. V1 equals, remember Ohm's law, V equals IR, so this would be ILR1, and this V2 can be IRR2, to eliminate some variables there. So in this case, again, we have 3 currents and 3, so we will need 3 unknown currents, but we need 3 equations. All right, so sometimes with these circuits, we can certainly write them in terms of the currents. Sometimes it's going to give us an integral, right? Because we have derivatives and stuff going on in here. Because the current is a derivative of the charge, and the voltage is related to the charge on the capacitor. And so we may want to write it in terms of Q's instead of I, so we have derivatives instead of integrals, things like that. But let's just go ahead and see what we get here. And so let's just do KVL around the left loop. Left. All right, so we'll start down here. We'll have negative V1. Well, that's pretty not too exciting there. And remember, the plus is the long bar on the source, and so we'll have plus 12 volts equals 0, or we can say ILR1 equals 12 volts, because V1 is ILR1, right? Anyway, there's one equation. And if we know the R's and we know the V's, it's pretty much solved there already. Let's try the more interesting side. KVL right, where the capacitor is. So let's go ahead and say the switch is closed. We're going to see what happens. And so we're going to have negative 12 volts starting on here. Coming around, we have plus VC. For the moment, we'll just call it VC. And then we have, coming around here again, we have plus V2 equals 0. All right, so we have negative 12 plus VC. All right, how can we write VC in terms of I? It's related to IR somewhat, but we don't really have an equation for that yet. Let's leave it as VC for a minute, and then V2 is I2R, IR, R2 equals 0. All right, what to do with VC? What do we know about voltage out on a capacitor? We got QVC, right? And so we can say V, this is for voltage of the capacitor, of course, is Q over C. But now, instead of having a V, we got a Q. Does that help anything? And so we could put this in Q over C. But what is Q? Or how is Q related to current? right? Remember current, what's our definition of current, is a flow of charge. So IR is dq dt, where q is the charge on the capacitor, right? And so I is dq dt, so the flow, the derivative of the charge is the current, right? And so what is q then? We got dq is IR dt, right? So q, run out of space, is the integral of IR dt. Okay, it's an equation, right? I said we didn't have to solve, we'll be happy. So we got negative 12 volts plus VC, which is Q over C, right? So, which is this integral times integral over C, or 1 over C times the integral of I sub R dt, and then plus IR R2 equals 0, right? So VC is this guy. So here's one equation. Oh, we need 3. We got just 2 so far. And this equation. And if we wanted to, take the derivative of this whole thing, we could make it be a differential equation instead of an integral equation, and it might be easier to solve, but again, we're not worrying about solving. But we need one more equation. So we did some KVL, so let's do a KCL. Let's identify the nodes here a minute. So here we've got all of this is a node, right? I was connecting, assuming the switch is closed, and then down here is a node. Right? Nodes extend until you hit something, right? And then this is a boring node because it's only connecting 2 things, but it's technically a node. All right, so we've got 2 nodes that have 3 and 1 that has 2, but this one is kind of pointless because it just says IR equals IR for what we've written. So let's just do KCL on the top. And so KCL on the top, we've got coming into this node, out of the source, into the node is IS. And that's the only thing coming in. And then IL goes one way out, and IL comes out down through the resistor, and IR comes down through the capacitor, plus IR. All right, so that gives us our third equation, and we should be good. Just to prove that we can run into equations that don't help, if we do KCL at the bottom, what do we get? What's coming in? We've got IR coming in, and we've got IL coming in, and what's going out is IS, which is the exact same equation we have here. So that doesn't help anything. Doesn't give us one more equation because it's a redundant, or it's not linearly independent from the other equation that we already had. But thankfully we already have 3. One's a differential equation, but that's okay. All right, so we're going to go ahead and stop there. That's good.